Okay, so I would like to thank for the invitation, and it's my second time here, and it's a very nice environment, of course, and I went to see who are the names of famous professors in Collège de France that were until the 1860 or something like this. There is a big patio over there, and to look for someone important and or someone I knew, and there is a Polish poet, very important Polish poet, who was a professor here in between 1840 and 1852. Okay, so it's a very special place indeed. So what I will talk about is a program that we carried out with my postdoc Yong Liu and with Frank Packard. And also some of it we did with Manuel Del Pino and Zhongcheng Wei. So there are several papers that I will talk about. And the purpose of this program basically was to try to understand certain class of entire solution of certain nonlinear elliptic PDE. And so the type of equation, I call it Allen-Kahn, but people call it also bistable equation, or maybe even Ginzburg-Landau. There are various names attached to this equation, but the equation is a very simple one, and it looks simple. It's Laplacian u is equal to nonlinear function. That nonlinear function is u times u squared minus 1. And I think on this picture I put u times, yeah, that's probably it, yes, this is the function. Yes, exactly, this is the function. So the blue one, or the bluish, is the nonlinearity, and it this equation, in fact, you can think of it as equation that comes from the Euler-Lagrange equation for some energy functional. And with that energy functional, the energy density will have a gradient term and the double well potential. So this is the double well potential. And the important thing about the nonlinearity is that the area under the blue curve is equal to the area under the blue curve here. So these two areas are equal. This simply comes from the fact that the potential is double well with the two wells of equal depth. So, and this is very, very crucial. Now, some of the results that I will talk about can be generalized very easily to other nonlinearities as long as they come from some sort of double well potential. So they are derivatives of double well potential, not maybe all of it. But this nonlinearity is in some sense the most, well, this is the most important among all these nonlinearities. Let's put it this way, okay, in some ways. So this is the plot. So the simplest thing to look at, of course, is the one-dimensional problem. So look at the ODE. This ODE, with what I'm interested in are solutions that behave asymptotically as constants, because well, the double well potential in fact has two trivial states. So immediately, always 1 and minus 1 are solutions to this equation. Okay, and they will be energetically there will be minimizers. And so my interest is in solutions that somehow connect between these two minimal states, okay, but they're not trivial. And so the first thing to look, as I said, is to look at the ODE. And so the ODE, you look at solutions that behave as plus and minus infinity in this way. So they go to the constants, plus and minus 1 respectively. And let's say we look at, so we fix, because everything you can translate, so we fix the value at 0, or we say that solutions we are interested in are odd, okay? And then there is a solution you can compute explicitly. It's the hyperbolic tangent, okay? So now what I am interested in are solutions of this problem, but in higher dimension. So in higher dimension, you can lift one-dimensional solution to higher dimension very easily. You just take u of x as the heteroclinic solution that I called heteroclinic, this h, with plus and minus. It doesn't matter. You can change signs. And then you take an affine function, okay, an affine function. So let me show you a picture how it looks like in 2 dimensions. So this is the heteroclinic, okay, the hyperbolic tangent, and this is the graph of one example of this function u of x and y in this case, which is the heteroclinic lifted to 2 dimensions. Okay, this is an affine function, exactly like you see. Okay, and this solution goes from -1 to +1, and it changes sign along a straight line. Okay, so it's along a straight line. So this is we call a planar solution. Okay, it's the simplest higher dimensional solution that there is. And as I say at the end here, this type of solutions always have certain monotonicity. That is, the direction derivative along the direction orthogonal to the nodal set, okay, will be positive or negative. Well, depends how you take it, but will have a sign in any case. Okay, and you can see on this picture, of course. So there is a conjecture or a problem related to called known as the Georgi conjecture. The Georgi conjecture says that any smooth and bounded solution to the Allen-Kahn equation, which is monotonic, okay, in some fixed direction, must be exactly the planar solution. So it's the heteroclinic of an affine function. Okay, and this should be true at least when the dimension of the space is less or equal than 8. But there is no traveling wave in this problem because the nonlinearity is balanced. This is exactly the point. This equation in this sense is more rigid. It doesn't allow you to connect anything with anything, just -1 and +1, and that's it. Okay. It turns out that this is true as stated. That is up to dimension 8, and the proof was done by several people successively basically the late, I think, 2000 and between 2000 and 2000, maybe late 90s until 2006, 2008, something like this. Gossup and Gui proved it in dimension 2, then Ambrosi and Cabret in dimension 3, and these 2 dimensions are special, somehow easier. Dimension 2 especially is not so complicated. And then Savin proved the conjecture up to dimension 8 with some additional condition, which in fact people were, as far as I know, were unable to lift so far. So in a way, this is not completely satisfactory, but this additional condition, in any case, it's kind of mild. But it's not clear whether it's essential or not. And then in dimension 9 and higher, we constructed with Manuel Del Pino and Jungcheng Wei a counterexample to this conjecture. So my purpose actually is to study other solutions in 2 dimensions which are not monotonic. And so the question is whether there are interesting solutions in higher dimensions, different than this kind of one-dimensional solutions. So it turns out that there is a solution called saddle solution. It was discovered by Dank, Fife, and Pelletier around 94, which has the following property. So the nodal set of this solution are the lines x equal to y and x equals to -y. It is even, okay, and it is monotonic. So I will show you a picture. So on the left, this is a 3-dimensional picture. So it's a graph of this solution. So you see it's positive here, it's positive here, it's negative here, and negative on the other side. It has a kind of sharp transition between the regions where it is positive and negative. Okay, and maybe to visualize it better, it's good to write to draw a sublevel set. So let's say in this case, this is the set where the solution is negative, the green one. This is where it is positive, and the nodal lines are exactly the 2 straight lines. Okay, and this solution is symmetric; it's even, and it has monotonicity, but in a quadrant, not in the whole space. Okay, so I'll talk about this later, about this monotonicity and things like this. But it was a solution discovered by Dank, Fife, and Pelletier. In fact, to find such a solution is not very difficult. What you have to do is you have to you can do variational argument. You can make variational argument on a domain that looks like this kind of triangle, essentially, okay? And look for solution that is 0 here, 0 here, and Neumann boundary condition here. But you minimize, you find a minimizer, then you pass to the limit with this top of the triangle, and you find the solution, and then you reflect it. So this is not so difficult. But the question is whether there are other solutions, and I believe that for quite some time, so maybe we wrote this paper about 2008. For quite some time, that was not known whether there are other solutions, or we were not proved. I've never seen any paper on this. So we discovered, with Manuel Del Pino, Jungcheng Wei, and Frank Packard, we discovered another type of solutions. And these solutions are kind of surprising. So to explain them, one has to first explain what is the Toda system. So the Toda system is a system of K ODEs. Okay? This is a very important example of an integrable system that was studied by long time ago by Ulam and Pasta and other people. And in fact, I think Toda was the one who discovered that was an integrable, completely integrable system. And then there was some work on this, a lot of work maybe on this in the early 70s. In particular, Constant, and first Moser, and then Constant generalized the result of Moser, described the scattering pattern of this equation. In some sense, described all the possible asymptotic behaviors of certain class of solutions to this system of ODEs, and it turned out that they behave in a simple way. They are linear, always linear at infinity, okay, and minus infinity as well, with some exponentially small correction. So at the beginning, it's not completely obvious what is the connection of this with the Allen-Kahn equation. Okay, before I go to this, let me notice some very important property of the Toda system, which is the scaling. So if you rescale the independent variable with epsilon, and you add a logarithm times some constant, or that's not a constant, depends on the particle, okay, on the coordinate here, then you get a solution to the same problem. So this means what this rescaling does. This rescaling changes the slopes, makes the slopes smaller, so if you wish, mechanically, it makes the speeds very slow, okay, of particles, and it spreads them. So this is the scaling. Okay. So the theorem that we proved is that if you have a solution to the Toda system rescaled, represented by these curves Q epsilon j, okay, then you can find a solution to the Allen-Kahn equation whose nodal lines are gamma 1 epsilon, gamma k epsilon. And these nodal lines are basically the lines given by the Toda system plus a small correction. Okay? And in fact, you can write explicitly more or less the approximation, okay, of how the solution looks like, the profile. And the deviation from this will be exponential. At infinity, let's say when x is very large, the distance between this approximation and the true solution will be exponential. And notice that in this approximation, what is taken is basically a superposition of the heteroclinic solutions centered at this nodal lines. Okay, so I will show you a picture. K is any k. Any k. You give me any k, any number of that's the integer, of course. It's a positive integer. So let's say if k is 2, so if you have two lines, this is an example of a solution. So this solution goes from -1, then to 1, then goes back to -1. And you see that its nodal lines are slightly curved. They are not parallel. Okay, they are not parallel. And this is a picture. This is a nodal line 0. Okay, this is where the solution is negative, positive in between. They are slightly curved, like this. And these curves are precise. Well, they are asymptotically given by the solution to the Toda system, rescaled. Yeah, you have to rescale with epsilon. So the theorem depends on epsilon. It says when epsilon is very small, which means that we can construct solutions whose angles, okay, or slopes of these lines are very small. And they're, in certain sense, almost parallel.
Sorry, what is the limit when y
They go away from infinity. This distance is like the log of the slope.
Okay,
They go. There's nothing. No, it goes to. In this case, it will go to 1, because no, you mean at infinity here? Yeah, it goes to 1. Sure. To -1 and to -1 here. Yes.
Okay, and if you take k equal 3, if you have a
It changes signs. They will show you k equal to 4.
-1 and +1?
Yes. Well, let me show you what happens with 4, because I think I have a picture with 4. So with 4, you would say, let's say the solution is negative here, it goes to -1 here, positive here, goes far away to 1, because these lines, they spread. So it goes in between to 1, then in between to 1, in between to -1, 1, and -1 again. Okay, and along, if you take, this is what I will talk about later, if you take, let's say, this line locally, okay, and go far away, then the solution will look like the heteroclinic solution associated to this affine line, plus an asymptotically exponentially small correction. So their behavior at infinity of the solutions is very well described. It's kind of rigid. Okay, and so the method how to prove this is a Lyapunov-Schmidt reduction. So what you start with is you take a solution to the total system. You build out of it an approximate solution in which you add a free parameter, which is a function, okay, because you have to correct somehow. It needs exactly the solution to the total system is not going to be the nodal line. You have to correct it. Okay, and you have to also correct itself, this approximate solution, by another function. So in fact, this Lyapunov-Schmidt reduction is kind of infinite dimensional. There is an infinite parameter that depends that belongs to an infinite dimensional space, this function phi, and another which is the function h. Okay, and they solved later some linearized operators and things like this.
Sorry, I go back to this the point of k. In the examples you give, k is even.
You can take even. You can take odd.
K odd, but
yes.
not equal to 1.
No, 1 is the one that is the planar. That's the trivial.
1 is from the.
Yeah, it's the one that is trivial. Yeah. Of course, it is. There's nothing new. Okay, so this two basically results. Okay, the one of Dang, Pfeiffer, and Pelletier, and there was a result that I mentioned of Montechiari and his collaborators. They constructed subtle solution, but with many lines, but of a similar type, as one of Dang, Pfeiffer, and Pelletier. And what we did, okay, that leads basically to the following observation, okay, that any of these solutions that I described so far have the following property. The asymptotic behavior of the nodal set is described by a collection of 2k affine lines on the plane, okay, and to which you can assign directions. And you can assume that they are ordered. And along each of these half lines, the solution looks like a copy of the heteroclinic with plus and minus sign, far away, okay? So this is exactly how it looks like, with some exponentially small correction, okay? So for instance, you can take, hypothetically, let's say you can think of a solution that will look like this. Let's say in this red set, which is some compact set, in this case a ball, you don't know what it looks like, okay? There is no particular reason to think that it will look this or the other way. But outside, the nodal set of the solution will consist of these 8 affine lines, okay? In between, the solution changes sign, and far away along each of the lines, it looks like the heteroclinic, like the planar solution. Or it's negative, okay, because you have to glue plus and minus. Okay, the signs are alternating. Okay. So the fact that this is the number of affine lines, half lines, is 8, or in general it's even, this is not accident. It must be even. Okay, this is not a difficult argument. Okay, it has to do with, you can use analytic continuation and things like this, and prove that the number of these affine lines, we call the number of ends, must be even. Okay, so this leads to a definition. So the definition is any solution satisfying the two conditions on the previous slide will be called a 2K end solution, and we'll denote the space of these solutions by M2K. Okay, and so far what we know is that this space for any k, this space is non-empty. There you can always find a solution with 2k ends. So my objective is to try to understand now the space of solutions with 2k ends. So I'll go back to the previous slide, but before that I have to state a definition. So we call as an element in this space non-degenerate if the linearized operator around this element, okay, does not have a kernel. Let's say in the space of the exponentially decaying functions, or L2, it just doesn't have a kernel. Okay, and in fact, for any k, this space of 2k end solutions contains non-degenerate elements. So assuming that something is non-degenerate in the space is not an empty condition. Okay. So let me go back to the previous slide, and before I go further, let me, for instance, concentrate on this line, this affine line. So this affine line, what you can do is you can move it along the circle, okay? So that's a rotation, or you can translate it. So you can rotate it or translate it. That means to each of these affine lines, you can associate two parameters. So the number of lines is, in this case, 8. The number of parameters is 16. The number of lines will be affine half lines will be 2k. Then the number of parameters will be 4k, respectively. So what you may think is that if I find a solution that, let's say, looks like this, has 8 ends, that perhaps I can perturb each half affine line by 2 parameters and find a solution nearby, which will be a perturbation of this one, but with 16 parameters. That basically would mean that the dimension of the space of solutions, at least near this one, is 16. It's the number of ends times 2. Okay? So this would be the natural conjecture. So let me say that this is natural, but it is not true. In fact, if you think about it, it's not completely natural. So as I say, that the space of 2k end solutions, for each solution in this space, you can associate 2k affine lines, which is a 4k parameter family. Okay? So you can think that this, for any choice of such 2k affine lines, perhaps you can find a solution. But this is not true. In fact, the directions are restricted. And so the theorem that we proved with Manuel Del Pina and Frank Paccard is that near any non-degenerate element of the space of 2k end solution, this set is a 2k dimensional smooth manifold. Okay? In fact, it's real analytic. It's not very difficult to prove that after you know it's smooth. Okay? This means that the directions of the lines are restricted. That's this. You can prescribe, let's say, arbitrary 4 directions. This one, this one, this one, and this one. But the remaining 4 will be already given, will be determined uniquely. So the freedom is less than you might think at the beginning. And then some ingredients of the proof. Okay, the proof is, in fact, is quite a bit of work. But it basically amounts to analysis of this linearized operator, okay? But in not the usual sense that normally what you do is you analyze in some L2 space an operator and you work in L2 space. In this case, because we need to consider perturbations of the solutions that are not in L2, you need to analyze the invertibility property of this operator in a bigger space. So let's say it will be the standard, more or less, space with some exponential decay or something like this. But to this, you have to add a finite dimensional space of functions that are not integrable. Okay, so this is quite a bit of work, and you have to understand the kernel of such operator and things like this in this bigger space. And then after that, you can use implicit function theorem to prove the dimension. Okay, to find the dimension. Let me mention also that there are restrictions on the directions that are not obvious a priori, but they are very important. And in this case, on the plane, there are two restrictions that come from the invariances of the problem itself. Okay, it's because every solution you can rotate or you can translate. So, okay, so these are in fact isometries of the plane. And to each isometry of the plane, you can associate the so-called balancing formula. So I'll explain what it is. But the basic restriction that you have always is that if the directions of the affine lines are given this way, then the sum of the vectors, so the sum of the forces, okay, pulling on the lines has to be 0, and sum of the torques, so the forces, let's say the radial force, no, that's not radial, angular, okay, or torques, sum of the torques also must be 0. Okay, and this comes from balancing formulas that are related to the translation invariance of the problem and rotation invariance of the problem. Okay, so these balancing formulas basically follow from this formula, which is a very general formula, and I point out here that was used. It's a version of a Pohozaev identity that was used by Shen and other people in geometry. This is a very important identity, and well, anyway, this is a very important. It's used to prove monotonicity formulas and things like this. In this case, it's kind of baby version of it. By hand, you can prove it. And so you have divergence of something is equal to 0. This x is the vector field associated to translation or rotation. Then you integrate, and you get this formula. And from this formula, one can deduce a lot of information about the behavior of the solution, okay, or its nodal set. If you take a big omega, okay, very big set, just because it is known, the solution is known to have certain asymptotic behavior. We can explicitly compute this integral. Okay, so that now I will talk about the special case, which is foreign solutions. So the foreign solution, the space, the dimension of the moduli space, the dimension of the space of such solutions is 4, is the number of ends simply. And then, well, in R2 you have 3 isometries, 2 rotations, 2 translations, and a rotation. So this accounts for 3 of the dimensions. So there is one dimension left, okay, in this space that is not accounted for by isometries. So the question is, what is the dimension? So what we know is that, okay, this space of foreign solutions contains non-degenerate elements. There are solutions we found with almost parallel ends. The saddle solution also is non-degenerate that we proved with Liang-Liu. And so based on this, one can identify 2 pieces of this space. Okay, one in which the angle between the ends is close to pi over 2, which comes from the saddle solution, and the other for which the angle is close to 0. Okay, and so the question is, are there foreign solutions whose angle between the ends is any angle between 0 and pi over 2? Okay, so this is not in some sense, this is not a precise question. So before I make this question precise, I have to refer to a result. Oh, well, I have to explain a result of GUI. Well, before that, let me recall you what the saddle solution looks like. So this is the saddle solution. Now I take the green set, let's say, to be the set when where the saddle solution is positive. So if you take derivative in the first quadrant of the saddle solution in the x direction, okay, it will be negative, and in the y direction it will be positive. So in this sense, it is monotonic on a quadrant, okay, and the solution is even. you can reflect it with respect to the axis. So this is a property, okay? This is not very difficult to show. This comes from the construction in some sense, okay? But the theorem of Gouy says the following. If you take any 4n solution, then there is a rigid motion or an isometry of the plane after which the solution will be even, okay? Or you have to multiply by -1 perhaps, will be even, and it will be monotonic in the first quadrant, in that sense that I described before. So its x derivative will be negative and y derivative will be positive. And this is very important because you can take the quotient of the moduli space by the isometries. What you get is what I call the space M4 even, that consists of even symmetric functions, monotonic in the quadrant. And we know from the previous result that this set is a smooth curve near each non-degenerate element. Okay? And not only that, what is more important is that from this result it follows that it makes sense to speak of the angle between the ends. Okay? So let me explain this. Let me explain this here and then I'll go back. So you take a 4n solution that we proved with Frank and Jungcheng and Manuel, okay, with 2 ends. And so the ends are almost parallel, but there is a small angle, okay? And that because of the monotonicity, you can always assume that the nodal line in each quadrant, the nodal set in each quadrant consists of just one curve, okay? It's a bigraph, in fact. It's a bigraph. And so therefore, it makes sense to define the angle of the asymptotic affine line of this curve and the x-axis. This will be the angle theta here. And for the saddle solution, this will be the angle here. Okay? And what we define, in fact, is not, we work not with the angle itself, but what we call classifying map or angle map, which is the angle minus pi over 4. So for this solution, the angle is minus pi over 4. For this, it is 0. And there is another solution which comes from rotating this one by pi over 2. And the angle will be close to pi over 4 in this case. Okay? So the classifying map is a map between on the interval between pi over 4 and minus pi over 4 and pi over 4. Okay, so I said any solution in this space is even symmetric and monotonic. Okay? They are also stable outside of a compact set, and that comes from the fact that they look like heteroclinic solutions outside of or some of them, a compact set. Okay? And then using this, we can prove, first of all, that all solutions in this space are non-degenerate. Okay? So that the space of 4n solutions is a one-dimensional smooth manifold. Okay? But now what we want to understand is how this manifold looks like. In particular, how many components does it have? Okay? As I said, the nodal set of any solution can be, to the nodal set of any solution, we can associate a classifying map, which is simply the angle that the nodal line in the first quadrant asymptotically makes with the x-axis. Okay? Minus pi over 4. That's the classifying map. And this classifying map goes, as I said, from minus pi over 4 to pi over 4. Okay, this is the picture. So and the theorem that we prove, that this all work with Donglu and Frank Paccard, is that if you take the angle map on that space, it is proper. That is, the pre-image of a compact is compact. Okay, and this is always the basic sort of tool to have in order to understand some sort of rigidity result, okay, for this kind of space. So it may happen, okay, that this moduli space contains several components. Some of them are compact and some of them are not compact. Okay, but what we can look at is the component that contains the saddle solution. Okay, and this component is in some ways very special. The saddle solution is very special because it's unique, and so using this, we can argue that this component cannot be compact. So it must be diffeomorphic to R. Okay, must be because of this theorem must be diffeomorphic to R, and this means in particular that the component of the moduli space that contains saddle solution contains solutions with any value of the classifying map between minus pi over 4 and pi over 4. So the classifying map is surjective. Okay? But you may have connected components that are not diffeomorphic to R. That's a possibility. So we proved that in fact it is not possible. That is, every component in this space is not non-compact. All components have to be diffeomorphic to R. So, okay, so these are the elements of the proof, and the proof is slightly involved, but not so much. It's based on many previous results, of course. It uses the result of Berestyk, Caffarelli, and Nirenberg. Uses the de Giorgi conjecture in dimension 2 in a key way, and the result of Gui, okay, and then the balancing formulas that I mentioned that allow to control the angles, and also partial classifications of the Jacobi fields, okay, in the linearized operator. Okay, but this still does not exclude the possibility that there are many non-compact components in that space. So there are many. That's it. So there are many disconnected components. Okay. So what we proved finally with, and that was another paper with Yongliu and Frank Packard, is that in fact the connected component that contains the saddle solution is unique. So there are no other components. So the proof is based on the fact that you take this component and you can deform the saddle solution to a solution with any small angle between the asymptotic line and the nodal line and the x-axis, and then you can show that then this solution is one of the solutions that we found in the very first paper with that I mentioned. It's based on the Toda system. Okay. So as I said, I don't want to go too much into this. So any solution in this space is a continuous deformation of the saddle solution. So in particular, it follows that if I take this solution, okay, with two lines, so 4 ends, 2 lines, I can deform it continuously in the space of solutions and get to this solution. Okay. So let me say that this theory has a connection, okay, and with the theory of the so-called Scherk surface. Scherk surface is a minimal surface, which is it's a periodic surface. I will show you graphs in a second, and it's given, for instance, explicitly in this way. This is an implicit, okay, way of giving the Scherk surface with a parameter theta, okay, that I will explain. So let me show you the picture. So these are 2 examples of Scherk surfaces. Here theta is pi over 4, and here theta is something else, some small angle. So you see the Scherk surface has 4 ends. The minimal surface has 4 ends which are planar. Okay, so let's say this surface, you can imagine that at infinity it looks like 2 planes that cross at the right angle. And this one at infinity looks like 2 planes that cross at some small angle. Okay? But the intersection between the planes is what we say desingularized in such a way that this surface is embedded. Okay? So this is an embedded minimal surface, and you see that this necks here, okay, or these tunnels, they look like catenoids. So this is a piece, some limit, okay? It's a piece of a catenoid, and the one that goes here, it's also a catenoid. And in this case, the angle is pi over 4, and these 2 catenoids are the same. But in this case, you see that this catenoid in this tunnel is very narrow, while this one is very wide. So they're not the same. When you change the angle, the bridges change. Okay? So the Scherk surface was discovered by Scherk himself in 1800s, okay? It was the time of Cauchy, and after the July Revolution, I think, a long time ago. And then Karcher found, because Scherk found just the surface with the angle, the right angle. Then Karcher found in the 80s, okay, all the other examples with any angle. And this is not so, well, again, the minimal surface theory you always rely, and this is what you rely on many times, you rely on complex analysis. Okay? And this surface, Scherk surface is an embedded, singly periodic minimal surface with 4 Scherk or planar ends. So the question general is, if you have an embedded singly periodic minimal surface with 4 Scherk ends, what can be said about this surface? And the result of Mix and Wolf is that this must be a Scherk surface, and this result is parallel to the result that I showed, okay? But in the minimal surface theory. And so what you can do with Scherk surfaces, it turns out, and that was discovered by Treuzet in the late 90s, is that you can glue them together. So you can think of it like this. You have one Scherk surface, okay, and then far away you glue to it another one, and so on, and you build kind of tower of Scherk surfaces, okay. And this is what I'll show you how it looks like in my context. But Treuzet proved that you can find a surface that has the following property. You take a collection of vertical planes, you intersect them in any way, but at least so that not 2 are parallel and not 2 share common line, not 3 share common line. So you intersect any collection of planes like this, and then what you can do is each of these intersections, you can insert a piece of a Scherk surface with the right suitably chosen angle to desingularize the intersection, and this way you get what they call Scherk tower. Okay, so what we did with Jungcheng Wei and Liu and Frank Packard is we tried to prove an analog, but for this equation. Now this is basically this is the same equation as before, but you scale the space by epsilon. This has nothing. It doesn't change the problem because scaling back and forth, you get solution, okay? But it is basically what we try to find is what we call blowdowns of generic 2K end solutions, okay? And so to do this, you solve this equation, okay? And the result that we proved is that if you take a collection of straight lines, K straight lines, such that not 3 of them intersect at a point and not 2 of them are parallel, then you can find a sequence of epsilon and sequence of solutions to this problem, such that the nodal set of these solutions converges to the set, okay, to this collection of straight lines, at least over compacts, and over the domains into which these lines divide the plane, the solution goes to plus or minus 1. Okay. So let me show you an example. An example is a 6-end solution. So you have 3 lines, this one, and this one. They intersect, as I said, and you can find a solution that has, in the limit, okay, it is plus 1 here, minus 1 here, plus 1 here, and so on. Change the sign like that. And the proof basically consists of gluing. So what you do is you insert a 4-end solution with the suitably chosen angle at each of the intersection point of the lines. Okay, and this has to be done carefully. This is not so easy. Okay, you have to be quite careful, and there are some changes in directions involved and things like this. Also, it is not completely obvious at the beginning, and you can do it in a consistent way. That is, in such a way that the signs match correctly. Okay, because you have to have plus 1, plus 1, plus 1. Okay, and minus 1, minus 1, minus 1. The signs may not be correct in principle, but that's a proof. It's not at the end not a very difficult fact of graph theory that in this case you can do it. Okay, in this particular graph obtained this way, let's say, not exactly in only this. In any graph obtained by intersecting lines, straight lines like this, you can assign consistently. Okay, and so the last thing I wanted to talk about is another type of solutions okay, that are now solutions, but with infinitely many ends. So these are the solutions will be will be very unstable. The previous type of solutions, if you take linearized operator and you define Morse index in a natural way for this linearized operator, it turns out that the Morse index is finite. Okay, the Morse index is finite. But if you have a solution with infinitely many ends, the reason it is finite is that is because you have finitely many ends. But if you have infinitely many ends, solution must be unstable. The Morse index is infinite. But anyway, these are not maybe from applications point of view so interesting, but mathematically they are quite interesting, this kind of solutions. And one example of such solution is very simple. What you do is you go back to the ODE and you find that the ODE has a periodic solution with any period. So you can take this periodic solution and you put it on the plane. There will be a solution. And that solution will have nodal set that consists of infinitely many parallel lines that are vertical or horizontal, if you whatever you wish. But this, of course, is trivial. It's not an interesting solution. And so what we look at is an analog, okay, solutions that will be analogs of a surface, another minimal surface that's called Riemann surface. So Riemann surface, I think this picture is nice, but this is a little bit more explains better what is a Riemann surface. So Riemann surface is a periodic surface. Okay, it's periodic in the vertical direction, and it consists basically of parallel planes at infinity, of parallel planes that are connected by pieces of catenoids. And well, you see how they are connected. They are shifted. This one is shifted with respect to this one. And also, if you take intersection of a Riemann surface with a horizontal plane, what you will get is a circle. In fact, this is a property of the Riemann surface that classifies it in some sense. Okay, you get a circle. And notice this is well seen on this picture. Let's say this circle is obtained by intersection with one vertical plane, and this one on the other side is obtained by intersection with another vertical plane. This basically means that this vertical plane is slightly higher than this one. Okay, so they are slightly shifted. They are parallel, but they are not the same height. Okay, they are not at the same height. Yeah, in some ways, the Riemann surface is a very interesting surface because it contains in itself a plane, the catenoid, or it means Riemann surface itself. Also, in some sense, it contains a helicoid. So it contains the standard simply connected minimal surfaces. Okay, so in order to relate this, I will go back to the Toda system. But now what I take is the Toda system infinite. So this is called now Toda lattice. Okay, so the number of equations here is infinite. Okay, and it turns out that this system has a solution which is called soliton. Okay, and soliton is in fact explicit. This is also a completely integrable system. This is very interesting. Okay, and it's very important as well. A very nice theory for this system. So it has a soliton solution. Okay, and the soliton solution is a soliton that moves with a certain speed, depends on the parameter. I'll show a picture in a second of this. And also this Toda system, Toda lattice, has the same scaling property as the Toda system. You scale, in this case, the independent variable, okay, with epsilon, and you add log of epsilon, you get a solution. Now I put some constants here in order to relate this Toda lattice with the one that I need for my problem, okay? So I can get a solution to this problem. So let me, before I show you a picture, let me say that the soliton solutions to the Toda lattice are related to the soliton of KdV, okay? And because if you take what is called the displacement profile of a soliton, and you take some special limit, then in the limit this function converges to one soliton, okay, to one soliton of the KdV, standard KdV. So this is how the soliton for the total lattice looks like. So I drew a picture here for k equal I, or I think I equals 0, 1, and 2, minus 1 and minus 2. Okay? And this is what it looks like after scaling. So I say that you can scale. You scale with epsilon, okay, and what it does, it spreads these curves. And you see they're not vertical. This is periodic, okay? This is periodic, but not in the vertical direction, but in some slanted direction. And also these are odd functions. This is odd, okay? It's odd and periodic. And so the theorem that we proved with Yongliu, Frank Packard, and Zhongcheng Wei is that if you have a solution to the total lattice, then you can find a solution to the Allen-Kahn equation. I'll show you in a second how it looks like schematically, which is periodic with some period, but it's not vertical. The period is not vertical. It's some slanted period, okay? And also it is odd, okay? So it does not come, because of this, it cannot come from the trivial periodic solution. It's something different, okay? And schematically it looks like this. So you take, these curves are the solutions to the total lattice spread, okay, scaled. And then the solution to the Allen-Kahn equation is, let's say, positive here, negative here, positive, negative, and so on. Okay, change the sign like this. It's periodic in this direction, and also it is odd. Okay, so I'll stop here. Thank you.